back to the discussion of WKB approximation. So now we can discuss about the general formulation of WKB approximation. So remember, WKB approximation is applicable for one dimension time independent problem with slowly varying potential. Okay. So if you have a potential V of x is slowly varying compared to the de Broglie variant, then the WKB approximation is applicable. Okay. So for that, you can recall our one dimensional Schrodinger equation. One dimensional Schrodinger equation is given by minus h bar square by 2m d square psi by dx square plus v of x psi of x equal to p into psi of x. Okay. So if you rearrange it, I can write d square psi of x by dx square equal to minus 2m by h cross square e minus v of x into psi of x. Okay, now 2m by h bar square e minus v of x. Now 2m into e minus v of x can be identified as the classical momentum square. Okay. So 2m into e minus v of x can be identified as p of x, and p of x is a classical momentum. Because E minus V of x gives the kinetic energy, so kinetic energy 2m times of kinetic energy is simply momentum, or so momentum square, so p square, because p square by 2m is nothing but the kinetic energy. Okay, so then I can rewrite this equation as d square psi of x by dx square equal minus d square of x by x cross into psi of x. So this is the general Schrodinger equation for a one-dimensional problem. Okay. So here p of x is nothing but square root of this, which is can be called as a classical momentum. Okay. Now here I can apply the WKB approximation if the potential is slowly varying function. Okay. So if v of x is slowly varying, then the possible solution of the wave function psi of x, I can write some amplitude a of x into a spatially dependent function, so I can write that as phi of x. Okay, so I am going to write in this particular form. So for that I am referring the textbook of quantum mechanics by Griffith. Introduction to quantum mechanics by WKB. Okay, so there are many textbooks available in quantum. This is one of the good textbooks. You have a good physical idea about the problems. Okay, so I am using the notations of the David J. Griffith. So if you have any doubt, you can refer that textbook. Okay, so if v of x is slowly varying function, then the wave function can be treated as an exponential function or harmonic function. Okay. So that depending upon how the energy and potential and all. So we are going to discuss a general formalism. So we can discuss the different cases later. Okay. So for the time being, I am writing a wave function of this particular form. Then what will be the first derivative of wave function? d psi by dx. Okay, so there are two functions of x, one is a, one is phi of x, so I have to use the product rule. Okay, then it would be dA by dx into e raised to I phi of x plus, next I have to keep a of x constant, a of x into I phi of x into e raised to I phi of x. Okay, so e raised to I phi of x I can take it outside commonly. So this becomes dA by dx plus a of x I into a of x into phi of x e raised to I phi of x. So that is the first derivative. Now next I can take the derivative of psi d psi by dx again, then I will get the second derivative that I can substitute. Okay, so that you can do it yourself. So please try to do it yourself, the second derivative of the wave function. So have you found the second derivative of the wave function? I can see the second derivative of wave function. If the wave function take the form a of x e raised to I phi of x is d square a by dx square minus a d phi by dx square plus I times this quantity into e raised to I phi of x. Okay. So why I have written this is I have divided this into a real part and an imaginary part times e raised to I phi of x. Okay. Now I am going to apply these two equations in our original Schrodinger equation. So the Schrodinger equation, the one-dimensional Schrodinger equation is given by d square psi by dx square equal to minus d square of x by x cross square psi of x. So just substitute the above two terms here. Then what you will get? The left side become d square a by dx square minus a of x into d phi by dx square plus I times 2 into dA by dx into d phi by dx plus a into d square phi by dx square into e raised to I phi of x equal minus b square of x by x cross square a raised to a of x into e raised to I phi of x. Now e raised to I phi of x is common on both sides, so that will cancel. So what is remaining is this is the equation. Okay, now this equation can be divided into two parts because we have a real part and an imaginary part. The real part and the imaginary part must separately equal, but there is no imaginary part on the right side. So therefore this imaginary term must be 0 separately and this term must be equal to minus b square of x by h cross square. Okay, now I can equate the real part and imaginary part. So what I will get for real part? The real part will become d square a by dx square minus a of x d phi by dx square equal to minus b square of x by x cross square into a of x. So that about the real part of the problem. And what about the imaginary part? 2 into dA by dx into d phi by dx plus a into d square phi by dx square equal to 0. So this comes through the imaginary part of our original Schrodinger equation. Okay, now we can start with the imaginary part. Now if you look at this imaginary part, this can be written in a very compact form as the derivative of a square of x into d phi by dx. So if you have doubt, just do it using the product rule. So what will you get is 2 dA by dx into 2a times dA by dx d phi by dx plus the next term would be a square d square f by dx square. 1a will cancel and we will get this result. So this you can do it yourself. So remember this a is a function of x. Okay. So since the derivative of a square d phi by dx is 0, so that means this term must be a constant, and I can write my a square of x d phi by dx must be equal to some constant, or a, the amplitude of the wave function must be equal to 1 by root of d phi by dx. Okay. So now I got a relation between the amplitude and the phase of the wave function. So remember, this is my wave function psi of x, where a is the amplitude and phi is the phase, and they are interconnected using this equation. Now the other thing is, you can look at the real part of the Schrodinger equation. Now in the real part of the Schrodinger equation, there is second derivative of a. Now recall, the WKB approximation is valid only for slowly varying potential. So if the potential is slowly varying, both functions amplitude and phase must be slowly varying. So if it is slowly varying, then its first derivative must be very small and second derivative must be even small. So that means d square a by dx square, right? D square a by dx square must be very small quantity. Or in other words, the second derivative of amplitude must be very small or very negligible compared to the second term. Okay, so that is an approximation. Okay, so that is again basically come from the WKB approximation. So using the WKB approximation, I can write the second derivative of the amplitude must be very small compared to a of x into d phi by dx square. So this is an approximation. Now using that approximation, this real equation I can write as a of x d phi by dx square equal to, or that's a minus sign over here, minus e square of x by h cross square into a of x. So minus cancels, a of x cancels. So what I will get? D phi by dx equal to p of x by h cross. So d phi by dx equal to p of x by h cross, or phi of x is equal to 1 by h cross integral p of x dx. So phi of x I can write 1 by h cross integral p of x dx. And what will be amplitude then? The amplitude a of x I can write, okay, so there should be some constant over here, c. So a of x I can write c by square root of p of x. Okay. Now there should be an h cross. The h cross can be absorbed in c. Okay, so I am just neglecting the h cross here. So this would be the form of the amplitude. This must be the form of the wave, the phase of the wave function. Now in WKB approximation, how can I write my wave function? So I can write my wave function psi of x is equal to some c by root p of x e raised to I by h cross integral p of x dx. So this would be a general form of WKB wave function. Okay, so next we can discuss the two different cases of WKB. That is, there can be allowed region, classically allowed region, and there can be classically forbidden region. And only one difference is, in classically allowed region, the wave function will take the same form, but there can be plus or minus term here. The exponential can be of plus phase or minus phase. So there can be plus or minus. So plus represent it's moving forward, and minus represent the particle moving backward. So there can be plus or minus symbol if you go for the classically allowed region. And in the classically forbidden region, this become exponential. Therefore there will not be any I term present here. It will become simply a plus or minus 1 by h. So that is the only difference. So I will write down the WKB wave function for the both classically allowed and classically forbidden region. So for that, I think better we can link this portion. So with this we have got the wave function in the WKB approximation. So in WKB approximation, the wave function take this particular form. So it is very simple wave function. Okay. Now if you look at a mod square of the wave function, mod square of the wave function. So mod square of the wave function will take the form mod c square divided by P of x, mod c square divided by P of x. So remember, the mod c square is a probability density. So this is the probability to find a particle at the location x. Now here, if you look at this expression, the probability density is inversely proportional to the momentum, and it is a classically non-thing for us. If the momentum is very huge, then the probability to find the particle at one particular position would be very less. So the probability of finding particle at one particular position is inversely proportional to momentum. It is simply a classically non-thing. And we are getting that expected result in the WKB approximation. The mod square of the wave function, the probability density of the wave function is inversely proportional to momentum. Okay. Now we can summarize what we have done till now. Okay. So we have got the wave function in the WKB form. In the WKB approximation, this is a wave function. Okay. And mod square, the probability density of the wave function I can write is inversely proportional to momentum. Now there are two different cases. In the WKB approximation, there can be a forbidden region and there can be classically allowed region. Okay, so both I can write down the WKB wave function for both the regions now. So case 1, first one is classically allowed region. So in classically allowed region, total energy is greater than the potential. So in the classically allowed region, the wave function or WKB wave function psi of x, how can I write? Okay, so there can be two terms, there can be exponential plus term and exponential minus term. So we can write the more general wave function for the classically allowed region. So I can write this c plus by square root of P of x, the e raised to I by h cross integral P of x dx plus next would be c minus root P of x, the exponential of minus I by h cross integral P of x dx. So there can be two independent solutions available for the same problem. So I can write both the possibilities. There can be e raised to plus I term and e raised to minus I term. So there are two independent function possible, and the corresponding coefficients I just denoted by symbol c plus and c minus. That is already you can put yourself. If you want to put b, c, d, whatever be, you can put the symbols that you like. Okay. So since I am referring the Griffith textbook, I followed the same notation. Now in the case 2, so in case 2, it is a classically forbidden region. So in classically forbidden region, what happens is that p square will become negative and t will become complex. So what I have to do is, in classically forbidden region, which is the total energy lesser than the potential energy, what happens is this harmonic term, the harmonically varied function, will become an exponential function. So this side WKB of x. So what I will write is, I can put some b plus divided by square root of modulus of P of x into e raised to 1 by h cross integral P of x dx plus b minus square root of modulus of P of x e raised to minus 1 by h cross integral P of x. So there can be two exponential, the positive exponential, negative exponential, that depending upon your boundary condition. So if the x is going up to infinity, then the positive exponential is not possible. Okay, but if the x is going to minus infinity, then the negative exponential is not possible. Depending upon the boundary condition, I have to choose which one is applicable there. But in certain situation, both the term may be present, because so for example, if x is neither going to minus infinity nor going to plus infinity, then both term will be present. The basic idea is the wave function must be normalizable. Okay, so it should converge, it should not diverge, it should converge. So when it going to infinity, that wave function should vanish, it should become 0. So based on you can put the value of d plus and d minus. So while solving the problem, we will understand how to write the value d plus and d minus in different cases. So this is the wave function in WKB approximation for the classically forwarding region. That would become a positive exponential function, negative exponential function, and if you look at here, I have written the mod p of x in both the region, both in d plus and d minus. Okay. So with this discussion, we have completed the discussion of the general formulation of WKB approximation. Okay. Now the thing is, you have to remember this wave function is valid only in the classically forbidden region and classically allowed region if it is far away from the classical turning point. So these wave functions are not valid if E is approximately V of x and they are called turning points. So the problem around turning points has to be dealt separately. So that we will discuss in next class. So the problem of dealing turning points will call the connection formula, that we will discuss in the next class in detail. And moreover, we also have to discuss what is the validity of WKB approximation. So these are the two things remaining for us: the validity of WKB approximation, and the second is the dealing of turning points. It is through the connection formula. Now both these topics we will discuss in the next class. So thank you.